A single machine, 225 meters long, 14,200 tons, drawing 16.56 megawatts of continuous power, operated by a crew of just 5. The Bagger 293 removes millions of tons of material each year from Germany's Hambach mine. On one day in 2005, it moved 380,000 cubic meters in a single shift. How something this enormous achieves that precision traces to an engineering lineage a century in the making. In the early 1920s, the first bucket wheel excavators appeared in European strip mining operations. These early prototypes, constructed by Morrison Knudsen and Dredge and Cole, featured wheels less than 5 meters in diameter and managed only a few dozen cubic meters per hour. Over the next decades, German engineering firms such as KHD and Siemens began to scale up the technology. By the 1950s and 60s, machines like Bagger 152 and Bagger 202 reached heights of 30 and 45 meters, respectively, as engineers Eric Rahl and Walter Joachim introduced larger wheels and more powerful electric drives to meet the growing demands of open-pit lignite mining. The late 1970s marked a turning point with the arrival of Bagger 288, a machine that stood over 100 meters tall and set records for daily overburden removal. Its 21-meter wheel and modular undercarriage allowed for continuous excavation at a scale previously thought impossible. The pace of innovation accelerated in the following decade as the reunification of Germany opened new markets and resources. By the mid-1980s, RWE's mining division, then known as Rheinbraun, commissioned a new generation of super excavators. Chief Project Engineer Dr. Klaus Johann Hartmann and structural analyst engineer Wolfgang Büttner led the blueprinting of what would become Bagger 293. Between 1985 and 1990, the team conducted feasibility studies and wind tunnel tests, refining the aerodynamics of the massive bucket wheel. Manufacturing began in 1991 at the Leipzig Kohlen plant, where more than 800 specialized welders produced the steel castings required for the machine's structural frame. Assembly commenced at the Garzweiler mine in 1995. Over the next 4 years, the components, some weighing over 30 tons, were transported and fitted together on site. The final commissioning in 1999 marked the culmination of nearly a century of iterative engineering. Reflecting on the process, Dr. Hartmann described the challenge as designing a moving city, where tolerances of millimeters mattered for a structure 100 meters tall. Each milestone in this lineage represents a deliberate response to the scale of Germany's lignite mines and the industrial need for uninterrupted, high-volume excavation. The result is a machine lineage that steadily pushed the boundaries of size, efficiency, and precision, setting the stage for the unprecedented dimensions and capabilities of Bagger 293. Bagger 293 stands as a structure that challenges ordinary sense of scale. Rising 96 meters into the air, its height matches a 10-story office building. The length measures 225 meters from end to end, enough to span 2 American football fields placed back to back. Standing alongside, a person appears as a mere dot at the machine's base, dwarfed by steel trusses and platforms that stretch in every direction. The footprint covers more than a full-size soccer field, with an extra third for good measure. Weighing 14,200 metric tons, the excavator is heavier than the largest passenger ships and outweighs a fully loaded Boeing 747 by more than 5 times. The main chassis supports this enormous mass on 12 crawler tracks, each nearly 4 meters wide. These tracks distribute the load evenly across the soft mine floor, allowing the machine to move forward at a slow, deliberate pace, roughly 10 meters per minute. Each track assembly is itself the size of a city bus, yet under the weight above, they appear almost insubstantial. Viewed from above, the machine's superstructure reveals a network of walkways, ladders, and maintenance bays. all connected by a lattice of steel beams. The central tower, nearly as tall as the Statue of Liberty, houses the operator's cabin and control systems. Flanking this core, massive booms extend outwards, supporting the bucket wheel at one end and the counterweight at the other. The entire assembly is engineered to maintain balance and stability, even as it moves and shifts during excavation. Every dimension of Bagger 293 is calculated to maximize continuous operation. The width, at 46 meters, provides a stable platform for the machinery and conveyor systems that snake along its length. The sheer volume of steel and concrete required for its construction rivals that of a suspension bridge. Each component, from the smallest bolt to the main support columns, is designed to withstand decades of cyclic loading, vibration, and exposure to the elements. Standing in the pit, Bagger 293 does not simply occupy space, it dominates the landscape. Its presence is measured not just in meters and tons, but in the visible transformation of the earth around it. The machine's colossal form sets the stage for the intricate systems and mechanical processes that enable it to remove millions of tons of material year after year. At the core of Bagger 293's operation is the 21.6-meter bucket wheel, a steel ring nearly as tall as a 7-story building. 18 steel buckets, each with a capacity of 15 cubic meters, are mounted around the rim. As the wheel rotates, each bucket slices into the pit wall, fills with overburden, and rises along the arc. Once a bucket reaches the apex, it tips its load into a transfer chute, feeding the material onto a conveyor belt. With every full revolution, the wheel lifts 270 cubic meters, roughly the weight of 200 mid-size cars. During peak digging, the wheel turns at 2.5 revolutions per minute, but average daily operation is closer to 0.6 revolutions per minute, balancing excavation with conveyor synchronization and routine maintenance. Material travels along a 2-meter-wide conveyor belt, running at up to 2.5 meters per second. This belt forms the machine's main artery, stretching more than 13,000 meters through the pit and out to the dump site. The system is engineered to handle continuous flow, with each segment built to absorb the shock of tons of earth dropping every few seconds. Tension monitors, magnetic rollers, and a network of sensors keep the belt operating at optimal speed, minimizing wear and preventing jams. Driving this cycle is a dedicated electrical infrastructure. Bagger 293 draws 16.56 megawatts from the grid, enough to power a small city. Yet, only a fraction of that energy turns the bucket wheel itself. The majority is consumed by the conveyor network, auxiliary drives, and control systems. The main wheel motor, rated at 300 kilowatts, accounts for less than 2% of total power demand. This distribution highlights an engineering paradox. The spectacle of the giant wheel is possible only because of the unseen, relentless current flowing through the machine's electrical veins. 5 people form the entire operating crew of Bagger 293 during a typical shift. Each member holds a specialized role: chief engineer, operator, mechanical technician, electrical specialist, and safety coordinator. The chief engineer monitors the machine's health and coordinates maintenance. The operator sits high in the control cabin, adjusting the digging depth and speed of the bucket wheel. The mechanical technician inspects tracks and hydraulic lines, while the electrical specialist manages the 16.56 megawatt power umbilical and backup systems. The safety coordinator oversees lockout procedures and environmental sensors, ensuring every movement complies with strict safety protocols. Crews rotate in 8-hour blocks, maintaining round-the-clock operation with only brief on-site rest between shifts. Despite the machine's scale, daily routines are methodical. Pre-shift briefings, belt tension checks, and scheduled lubrication of the wheel bearings. In the event of a power loss, the automated braking system can halt the wheel within 0.3 seconds, a feature tested regularly to prevent catastrophic failure. The ambient noise level approaches 115 decibels, requiring constant use of hearing protection and contributing to a sense of isolation among the crew. On July 18, 2005, Bagger 293 set a reported single-day extraction record of 380,000 cubic meters. The operator at the time described the cabin as feeling like a roller coaster, with the wheel turning without pause and the conveyor belt running at maximum speed. The safety coordinator noted that the emergency stop was tested at hour 18, confirming the system's reliability under peak stress. This achievement underscores both the machine's capacity and the precision required from the small crew. Yet the future of Bagger 293 is now defined by external forces. In 2019, Germany's Coal Exit Act set a federal deadline for lignite mining to end by 2038. Environmental campaigns and legal actions have intensified, with activists calling the excavator a symbol of fossil fuel excess. The looming phase-out places the world's largest excavator at a crossroads, its operational days numbered by policy rather than engineering limits. Today, the Bagger 293's 14,200-ton frame, 21.3-meter bucket wheel, and 16.56 megawatt appetite remain unmatched in industrial extraction. As global resource demands shift and mining regulations tighten, the benchmark for engineering efficiency evolves. Precision on this scale is still the measure for what's possible in mechanized earthmoving.